In this video, we're going to look more closely at neutralization and dissociation reactions, which are both types of acid and base reactions. Let's start with neutralization. So neutralization reactions bring together an acid and a base to form a conjugate acid and a conjugate base. While acid will have a low pH, and we'll talk about the pH scale here soon, and our base has a high pH, when we combine these, they'll neutralize to a neutral pH, and that's where that neutral language comes in here. And so this is what we think of as our standard acid and base reaction. And what's really happening here is that our acid, hydrochloric acid, is producing H+ ions. And NaOH should look familiar from when we talked about ionic compounds. If we dissolve this in water, it's really sodium ions floating around and hydroxide ions floating around, dissolved in water. So this is really producing a hydroxide ion. And together these combined and form a water molecule. And so the format for a lot of neutralization reactions is that their products are always water plus some type of salt. In this case, it's sodium chloride. Now within this, it's sodium chloride aqueous. So again, we know from ionic bonding that this means that there's really a sodium ion dissolved in water and chloride ions dissolved in water. And when we think about the conjugate base, we're really thinking about the chloride ion here, because our chloride ion is the one that has lone pairs all around it that are more available. Our sodium ion does too, because it's in that neon, it has a similar electron configuration, or valence electrons as neon, but our chlorine with the negative charge will be act as a base much more because of that negative charge, because it would benefit from forming a bond to a hydrogen proton to have an overall neutral charge. And so this is the foundation. This hydrogen plus hydroxide to form water is the foundation of our acid-base reactions. And let's talk about water a little bit more. It's what we call an amphoteric substance, amphoteric, which is a fun word. And that means that an amphoteric substance can either act as an acid or as a base, so both. It means it can donate a hydrogen. It can also accept a hydrogen. So that means it's definitely going to have lone pairs, no matter what, so it can accept a hydrogen. And it's going to have a hydrogen that can break a bond. So it'll have a hydrogen it can donate. And water is the perfect example of this. There's more amphoteric substances than just water. But in water, we have an oxygen bonded to a hydrogen, which is a bond that is particularly susceptible to breaking. So we can break this bond and we can lose a hydrogen, and we would be left over with OH minus, or hydroxide. And we also have these lone pairs right here that can actually form a bond to an H+ and form hydronium ion. So water will behave as an acid, and it will also behave as a base. And what dictates that behavior is just what it's nearby. If you put water near an acid, it'll act like the opposite. It'll be a base. And if you put water near a base, it'll act like an acid. And because of that, we have a type of neutralization reaction that we actually call a dissociation reaction. And it's adding an acid or a base to water. And water will act as whatever it needs to be, an acid or a base. And it's how we're going to later measure how acidic or how basic something is. So in our first example here, we have hydrochloric acid. There's a hydrogen here bonded to a halogen, and so that's an acid. And we have water. And because water is being combined with an acid, it will act as a base. And when this happens, that hydrogen atom on our hydrochloric acid, forms a bond with a lone pair on our oxygens, and that gives us our hydronium ion, which is our conjugate acid. And that leaves us with just our chloride ion, and it has these 4 lone pairs and a negative charge, so this is our conjugate base of our dissociation reaction. And we call this an acid dissociation reaction because the non-water reactant is an acid. Now, if the non-water reactant is a base, then we'll have a base dissociation reaction. So NH3 is a base. It has a lone pair on the nitrogen. And if we put it in water, our water will act as an acid. And so it's changing roles based on what it is combined with. So in this case, the water, instead of accepting a hydrogen, is going to do the job of donating it. And it's going to donate it to that lone pair on our nitrogen in our base. And when that happens, we're going to be left over with just this hydroxide ion here as our conjugate base. And our nitrogen gains a hydrogen, so we went from 3 NH3 to NH4 and gained a positive charge. And we form a conjugate acid. And we looked at this when we did Lewis dot structures. This is a nitrogen bonded to 4 hydrogens with a positive charge. So if asked to write a dissociation reaction, first identify if you have an acid or a base, then use water as the other reactant, and it'll act as the opposite of what you're starting with. And then predict the products and have water act as an acid if it's being combined with a base, and have it act as a base if it's being combined with an acid.